ओके, तो सबसे पहले जो है हमारे पास ये है क्लासियस इनइक्वालिटी. Classes inequality. Now, whenever a closed system undergoes a cyclic process, then you have this. Okay? ये हमारा जो है एक ऑब्जर्वेशन है which you find like this: del q by t is less than or equal to 0. Now, where del q is the amount of heat given to the system and T is the temperature of the system. इसमें we have to see that we have a system here, okay, and there is a surrounding here. So there is a temperature of the surrounding, right? And this amount of heat is being given to delta Q. Delta Q is being given to the system, and there is a temperature of T system. Okay? System should have one temperature throughout. Okay. Now, what temperature we are taking here is the temperature of the system. Otherwise ये error आ जाएगा इसमें, ठीक है. Whatever the temperature of the surroundings may be, if the heat is flowing to the system, because heat can flow either way, it can flow out of the system or into the system. If it is flowing into the system, T surrounding will be more. At the most, it will be equal to T system. And if the heat is flowing out, then T system will be more and T surrounding will be slightly less or much less than the T system. Okay. Now, what you have to take in this equation is T system. Okay, and we write it as T. Now, if this is क्या कहते हैं, if the process is reversible, okay, then what you get, del Q by del T, sorry, del Q by T is equal to 0. Okay, and if the process is irreversible, then you get del Q by T is less than 0. So actually you are moving in a cycle. You are moving in a cycle. You have a okay, and you move here like this, and you come back like this. Okay, 1 to 2. So you complete the cycle. Now I have shown this by a dark line, which means it is a reversible process. But same you can have a irreversible process. You can move from 1 to 2 via an irreversible process and come back from 2 to 1 via an irreversible process. Okay. So the important thing is you are making a cycle. This is 0. This is how you write. You complete the cycle. You start from state 1, you come back to state 1. And we are not bothered what is the process. It may be reversible, it may be irreversible. For both the process, we have the equation. If it is a reversible, then del Q by T integral over the cycle is equal to 0. If it is irreversible, then it will be less than equal to 0. Okay, this is the called Clausius inequality. Now we have to prove this Clausius inequality. This is the statement, and we have to give what is the proof of this. Or basis, what is the basis with us? That is the second law. So we have what we are basically doing is, we have a statement of second law, which I told you is a sum of all the experience we have had so far. So all the experience with the scientific community had, it has been concised or put in a single statement. And we assume that that statement is correct because so far no experiment has violated it. So that becomes our axiom. Okay. Whether it is true or false, we do not know because we have not tested it in all times and all places. We have not tested those laws in, let us say, out of solar system or in some other nebula, something like that, or maybe 1,000 years back, or what will happen in the future 1,000 years ahead. We are talking about that domain in which we conducted the experiment, right? And we find that that law is valid. Okay, it's quite possible. If you go to quantum physics, you'll find that in an instant something happens, some violations takes place, and then after that it goes away, right? So हम लोग तो क्लासिकल स्केल पे बात करते हैं. अगर हम टाइम को मेजरमेंट करेंगे तो वो मिनट्स में होगा, सेकंड्स में होगा, आवर्स में होगा. बट व्हेन इट इज milli seconds or pico seconds, so small time, what is happening we don't know, right? Why I am telling you is that you should get out of this sense that this is inviolable law. Okay, but then we should accept it also, because in the range we are doing it, we find it is true. So there will be people who will be working on breaking the second law. Let them. That is their job. They find, you can say, enjoyment in that. They find challenge in that. So there are people who are trying to break the Newton's law, Einstein law, Schrodinger equation, all that. There's people, they are challenging it. Yes, let them. Once they find out, we will accept it. And we are what? We are technocrats. We are using what is available. So what we start with is that it is true. Okay, and we try to implement. And in the process, if something comes out, no, it is not true. Okay, then we will join them. Right? So it's nothing like absolute कि ये absolute हो गया, ठीक है ना? तो हम वो openness जो है अपने अंदर रखें. ठीक है? That is why I speak many times about this, that this law is true so long as it is not violated. But anyway, so we are assuming, we are starting from the fact that the law, the second law is true. Okay. Now we are doing the corollaries of second law. That means mathematically now, if the second law is true, then these statements are also true. Okay. So we have stopped thinking about whether the second law is true or false. We are starting with an assumption that it is true. And then we find out certain more things, more statements we come across, which are true because the second law is true. Okay. And one of them is the classless inequality. So we are proving this. You make this diagram by the time I explain this, because this diagram perhaps you will not get in the books or in this form. Okay. What is this diagram is, we have a system here now, or you can say an engine also. Okay. Normally we show an engine by a circle. Here I have shown an engine by a rectangle, and because I am limited by the other parts of the diagram which I had to make. If I would have made a circle here, it would have become too big, or the drawing itself would become a difficult task. Anyway, so we take, this is a system, it's an engine. Now this engine is operating between different temperatures. We have a system which is a journal system. It may take heat at different temperatures and reject heat at different temperatures. So this system is taking heat at TA1, TA2 and TA3. So when it needs at TA1, it takes it at TA1. When it needs at TA2, it takes at TA2. When it needs at TA3, it takes at TA3. no problem. Similarly, it can reject at any temperature. Okay. Now, one thing we are doing is that whatever heat is required, we will bring from temperature T0. So we have a reservoir at T0. Now our system or engine is operating. It wants heat at TA1. So we will put a reversible engine here, a Carnot engine or a reversible engine here, and take heat at T0, get some work out of it, and generate heat at TA1 and give it to the system. Right? So originally we are taking all the heat from T0. Same thing for TA2, TA3, etc. And you can have n number of systems like in the series. Whenever you want any heat, this is the heat required. So system is requiring or the engine is requiring this heat, QA1, QA2, QA3 and so on. At temperature TA1, TA2, TA3 and so on. Now for each of this heat, we are getting it from reservoir at T0 using an engine like E1, E2, E3 and so on, converting that heat into a heat at TA1, TA2, TA3. In the process, taking out some work because our engine is reversible. We can do this. Okay. Now, same thing we are doing here, that whatever heat is being rejected to the surrounding, we are using a reversible heat pump and sending it back to T0. Okay, so whatever heat is available to us, we will give some work to it, use a reversible heat pump, convert it to another amount of heat Q01, Q02 and Q03 and send it back to T0. Okay, so heat pump is what it is doing. It is raising the temperature of heat we are supplying to it. And engine is what the engine is doing. It is reducing the temperature of the heat we need. Okay. And in the process, engines will give us the work and pumps will take the work. Now, if you put all of them together, you find that this system is working with only single reservoir. There is no heat which is going to the finally going to a reservoir which is other than T0. Whatever is required, you are getting from T0. Whatever is being rejected, you are giving back to T0. So if you put them all these engines together, E1, E2, E3 and the system S and P1, P2, P3, all the pumps together, what do you get? You get an engine in which it is operating with the you can say operating with a single reservoir. Now what does the Planck statement says? If a closed system is working in a cycle operating with a single reservoir, net amount of the work done is negative, okay, or zero. You cannot do any work. So what does that mean? That sum of all these works will be negative. So what do you get? W net will be equal to 0. Now what is W net? You sum up all the work done by the engines A1, A2, A3. You subtract all the work being done on the pumps B1, B2, B3 and P1, P2, P3. And what is the work done by the system? You add up all that. So this is the work you are receiving from the engine. This is the work you are giving to the pumps, heat pumps, and this is the work you are receiving from the system. Sum it up. That should be less than or equal to 0. Now, what is your WA1? WA1, if you look at it, WA1 this is equal to this, we are finding is equal to this minus this, first law. Similarly, WA2 will be equal to this minus this. Okay. And when you talk about WB1, it will be equal to this minus this, first law. Okay. And then you add it up. So what we are doing, we are converting WA1 to this sum of Q zeros minus sum of QAIs. Similarly, pump work is equal to sum of Q0, small Q0 i's minus QB i's. Okay. And this another work, this WS, the work done by the system, would be sum of all QAIs minus all QBIs. And in this, you will find that these two terms will cancel. And what you get? Sigma Q0 minus QI. This will be less than or equal to. This is the net work done by the system. We have not put any restriction whether the system is reversible or irreversible. Only the thing is our system is an engine. It's a cyclic system, so that nothing is happening to the system. Whatever is happening is to the surrounding, to the reservoir. Okay. So the net amount of work done is less than or equal to 0. Now, if you want to shorten this analysis, right, you can simply write the total work. All these work will be equal to the sum of these heats minus sum of these heats, because these heats are whatever you are giving to T0 and whatever you are receiving from T0. So you can directly write that also from the first law. So instead of finding the work for each engine and each pump and the system, you can say that the total work done will be equal to the heat received from T0 and heat rejected to T0, and you'll get this. So that is W. So there are two ways by which you can say, and you can say you see that you are getting the same answer that. So there is not different. Only thing is you're putting a different logic. In one case, you are taking care of all the engines and all the pumps and the system. And in the second case, you are putting all of them together. You are saying, okay, the net work done, because there is only one reservoir from which the heat is being exchanged. So the difference, whatever is the net amount of heat exchange from the one reservoir, that is equal to the work done. Okay. So this is the amount of heat received from the T0 reservoir, and this is the amount of heat rejected to the T0 reservoir. The difference will be equal to W net. Okay. Now what you can do, you can take this equation and use these equations. Now you remember that your engine at the tops are reversible and the pumps at the bottom are reversible. So you get this equation, ratio of heat transfer is equal to the ratio of temperature. And these are engines which are counted as series A1, A2, A3. And these are pumps which are counted with series B1, B2, B3 and so on. Okay. And both will follow this law because it's a reversible engine. And we have already done that for a reversible engine, the ratio of heat is equivalent to temperature, absolute temperature, ratio of the absolute temperature of the reservoir. Okay. So now what we can do, Q0I can be replaced by QAI by TAI into T0, and similarly Q0I can be replaced by this. Now this T0 is always greater than or equal to 0. Absolute temperature can never be negative. So T0 is greater than or equal to 0. So you can divide by T0, because in inequality, if it is an equation, whether T0 is negative or positive, you can always cancel it out, both sides. But if it is inequality, then for positive terms you can cancel on either side, but for the negative terms you have to change the sign. Okay, so our T0 is positive, so we can cancel it out on the both sides and without changing the sign of the inequality. So what we get is this: QAI by TAI minus QBI by TBI is less than or equal to 0. And what is this? This is nothing but if you replace these engines with an infinite number of engines. Now for each difference in temperature, you put another engine. So what you will get, del Q by T will be less than or equal to 0. ठीक है? This is what you get. तो ये जो है हमारी क्लासियस इनइक्वालिटी प्रूव हो गई. Now if your system is reversible, then the whole process can be reversed, because your all engines, वो जो आपने additional engines लगाए हैं, they are all reversible. All the pumps which we have put, they are also reversible. So if your system is reversible, then the whole system itself is reversible, which means that ये जो inequality है, इसमें अगर del Q हम माइनस कर दें तो भी it will be less than or equal to 0 for a reversible engine. Because if it is reversible engine, what will change? The sign of Q will change, not the sign of T. ठीक है ना? If you make sorry, if you make your engine as reversible, all the directions of heats are changed. So what was positive, now it will become the negative, and T remains same. So what do you get? Even this will be less than 0. Minus, and both plus and minus can be 0. So you already sorry, this is less than 0 and this will also be less than 0. Okay, sorry. So what do you get? That they have to be equal. They have to be equal. So what are you getting is that this integral is equal, and this is what is the Clausius inequality, that for del Q by T is for a cyclic integral is less than or equal to 0. When the engine is reversible, then it is equal to 0. When it is irreversible, then it is less than 0. ठीक है, तो ये जो है आपका क्लासियस इनइक्वालिटी प्रूव हुई. तो हाउ वी हैव प्रूव्ड इट? We have proved it assuming that the second law is true. The Kelvin-Planck statement. If a system is operating with a single reservoir, no positive work can be done. You can only, if you have only single reservoir, you can only give work to it, right? You cannot extract work from it using an engine, which means there is no other change except drawing the heat. आप वैसे तो कर सकते हो, आपके पास सिंगल रिजर्वायर है, कोई प्रॉब्लम नहीं है, then your system would not be cyclic. तो ये चीज आप ध्यान में रखिए. Kelvin-Planck statement we had talked about is that our engine is cyclic. Nothing happens to engine. Only thing is happening is we are drawing heat from the reservoir and rejecting to a reservoir. So the only change is happening is some heat is drawn from some reservoir, some heat is given to some reservoir, and we get work out of it. And then the Kelvin Planck statement says that if you have only one reservoir, so you cannot draw heat from it and get the work. The reverse is possible. You can use the work and give the heat to it. That's a simple thing. You have a work, you uh, do some friction with that, and heat is generated, which goes to the atmosphere. So you can do. The other way is not true. तो यही चीज से इस स्टेटमेंट से we have proved that Clausius inequality is true. Now, once we get this, what we are getting is the definition of entropy. Now, whenever a cyclic integral is 0, then what do you get? That for it is independent of the path. And if a property, if any parameter is independent of the path, you can easily define it as a property. So that means if this integral is 0, you can define a property. And incidentally, this has been defined as entropy. इसको हमने एंट्रोपी का नाम दिया. तो इसको कैसे प्रूव करते हैं? तो it says that in the corollary said there exists a corollary says that there exists a property entropy denoted by S of a closed system such that change in its value is equal to this. Okay. तो इसको प्रूव कैसे करेंगे? We take a cycle. ठीक है? There are two cycles here, A and A plus B is a cycle and A plus C is also a cycle. Now, the thing is all these processes are reversible. So this is a reversible cycle and this is also a reversible cycle. Okay. Now, as per the Clausius inequality for a reversible cycle, this is equal to 0, which means you can say integral A plus B and integral A plus C will be equal to 0. Okay. And then you can break it into two parts, A1 to 2, B2 to 1 will be equal to A1 to 2, C2 to 1. Okay. And both sides, this is common. Integral from on path A from 1 to 2 is same on the both. So what do you get? Integral on path B from 2 to 1 is same as integral on path C from 2 to 1. The condition what we have put, the process are reversible. If the process are reversible, right, then integral from 2 to 1 in both the cases B and C path they are same, which means that this is equal to a property. This integral is independent of the path. In other words, we may say there exists a property called entropy, and entropy is equal to this. Now you recall the definition given by that Boltzmann equation, S is equal to K ln N. So we have two definitions of entropy. Delta S is equal to del Q by T, integral from 1 to 2 across along a reversible path, and entropy is equal to K ln N. We have talked about it. We will talk about it again after this entropy thermodynamic definition is over. Okay. But note here that thermodynamic definition is talking about delta S. The statistical definition is talking about S. So the thermodynamics tells you the change in entropy, but statistical definition tells you the exact value of entropy. In thermodynamics, or I can say the statistical thermodynamics and this normal thermodynamics, engineering thermodynamics. So in engineering thermodynamics, you cannot find what is the value of entropy. Okay, you can find only the change in entropy. And we can do with it because we are really not bothered what is the exact value of entropy. We are only bothered what is the change in entropy. Right? Because we are talking about application. But in statistical thermodynamics, you can get what is the exact value of entropy. Incidentally, these two are exactly same. That is why they have been given same name. These properties are not different. The formula are different. On one side it is delta S, on the other side it is S, but S is same. So we are talking about the same entropy. And this is you can find here that convergence of statistical thermodynamics and this engineering thermodynamics. They are converging here. Now, then another statement I would like to make here, that to find change in entropy, if suppose you want to use this formula, so to find change in entropy between state 1 and 2, using this equation given above, we shall move from state 1 to say along a reversible path. If you have been asked to find the change in entropy, you can only move along a reversible path. So whenever you are doing this integral, for the purpose of finding the entropy change, first thing you should ensure that whether the path is reversible or not. If it is a reversible path, you can go very well on the path and do the integral. You will get the right answer. But if it is irreversible path, you will not get the right answer. You cannot go like that. But then what do you do? If there is a case in which you are told that you are moving from 1 to 2 by an irreversible path, find the change in entropy. What do we do then? The option available to us is that we know that entropy is a property. It's a point function. So we will devise our own path which is reversible from 1 to 2. So if the path given to you is reversible, but you find that it is difficult to find the entropy along that, somehow the path is complicated. Or if the path is irreversible, you cannot use the integral. In both the cases, you can find your own path to move from 1 to 2 and find the change in entropy. It will be same. So you need not go by the path given in the question or given by the problem. If it is irreversible, you cannot use that path. If it is reversible, it may be difficult path to carry out the integral. You can find your own simple path to find the. Okay, so this is as far as entropy is concerned. Okay, we still have some more things to discuss, but I just make a diagram here to make this point clear. Suppose you are given a problem like this, and the path is given like this. This is a PV diagram. 1 to 2. This is a polytropic process. Okay, or the better would be you take this process, which we know that TV like this. This is the polytropic process. This is a reversible process. You can find the change in entropy by moving along path A. You can use this path A. But why use this? You go like this. Find the change in entropy. You'll find it is easier. You go like this. First you keep the volume constant, then you keep the pressure constant. Your equations become easier. You can do it. Okay. So this is what I wanted to tell you. We will stop here. If you have any questions,